Hi, I'm Matt Evans from the University of Sheffield, and this is an overview of Theme 5 of Pipebots. So the Sheffield team is comprised of myself, Matt Evans, the postdoc on the project, with 3 academic team members and 3 brilliant PhD students at the bottom. Within the wider Pipebots project, we're one of the research-focused themes, developing a system for navigation, and we're working closely with the other themes, in particular Theme 3, Robot Systems, and Theme 4, Autonomous Control. So the broad goals that we have for Theme 5 are firstly to develop algorithms for mapping and localization in underground pipes. Secondly, we want to incorporate prior map information where it exists. And finally, later on in the project, we want to build multi-robot versions of our localization and mapping algorithms so that we can build, so the robots can cooperatively build maps of their pipe assets. The particular research problem that we have are of localization and mapping, whereas localization is answering questions like where is the robot right now and where it's been up to now, and then mapping is more questions like what are the robot's surroundings and what does the world look like to the robot. Often in robotics, the problems of localization and mapping are solved together in what's called the SLAM problem, simultaneous localization and mapping. And this is a bit of a chicken and egg problem. It's hard to localize yourself in a map and build the map at the same time. But breaking it down, it's essentially the problem of ego motion detection. So working out where you've been over time. So imagine the diagram on the left, you're going from A through C to B and drawing out this path. But then if you were able to detect loop closures, so recognizing that you're in somewhere you've been before, like the fact that B is close to C, you can build a coherent map and then use that for future planning. In the field of robotics, the SLAM problem is usually solved by large vehicles like the Stanley robot here, which was solved the DARPA Grand Challenge and went on to be developed into Google Street View. Essentially, you have a big vehicle so it can carry lots of very fancy sensors like laser rangefinders and LiDARs. And then you have a big boot full of servers so you can do lots of fancy compute. But the pipe environment presents all kinds of unique challenges. For example, you've got perceptual aliasing for one, which you can see here on the right-hand side. So this is 4 images of a pipe taken over a space of about 10 meters. And you can see they look really, really similar. So it's easy to get lost. Secondly, pipes are small, so you can't drive a car down it. You have to be much more careful in your choices of sensors and how much compute you can utilize. Also, the actual sensors themselves make a difference. So if you try to use a laser radar, some of the signals will be very, very close, so they'll be maxed out. And then some of them are effectively infinitely distance away because of the length of the pipe. So those sensors aren't really very useful. Also, the prior information is probably unreliable given that some of the pipe records are over 100 years old. And finally, we can't use GPS underground. At Sheffield, we focus on using visual methods because cameras are easily available and small, and focusing on methods like visual odometry. So this has been used in very challenging environments in the past, like on Mars rovers. So what you do is you extract image features and then in a succession of images and then track the movement of the features across the images and therefore infer how the camera has moved to generate those changing feature positions. Here we see an example of applying one of these visual odometry methods to a pipe CCTV inspection data. And you can see the features being extracted on the bottom left. The inverse depth is the color. And on the right hand side, you can see the main image, the trajectory of the camera being reconstructed in red and a point cloud map of the features in grey. And a lot of the work that we're doing is about testing how accurate these maps are. At Sheffield, we're also developing real-world test networks above ground so that we can test integrated software and hardware in a COVID-secure way. And our PhD students are developing research to help with some of the broader problems that we have in Pipebots. Rob Worley's developed a novel localization method, which we're hoping to be able to use with novel sensing methodologies that are developed in Theme 2, such as acoustic sensing and ultrasonic sensing, and also to be applied to the multi-robot case that I mentioned. And Seamus Edwards has been looking at using deep learning methods to extract manhole locations from Google Street View to provide some of that precious prior map information. So if you have any questions about any of this research, please get in touch with the team at Sheffield. Thank you.